Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using KNIME. As we mentioned, there are times when we see curvilinear data in the residual patterns and we're not able to perform simple linear regression. It is possible to achieve linearity through transformations of the data, and that's what this chapter is going to be talking about. So when a residual plot reveals that the data set is nonlinear, we can transform the raw data, which will allow us to use linear regression techniques more effective on nonlinear data. And so we need to walk through some of the variable ways that we can perform that transformation. An effective way to transform a variable usually just involves performing a mathematical operation. So there are two types. The first type would be to linear transformation that preserves the linear relationship. Therefore, the correlation between x and y would be unchanged. So for example, you could multiply x by a constant value, or divide x by a constant value, or adding a constant value to x would all be acceptable ways of preserving the relationship. A less desirable method would be nonlinear transformation. With nonlinear transformation, it's actually going to change the relationship between the correlation relationship between the x and y variables. So for example, taking the square root of x or the reciprocal of x. In that type of regression, a special kind of nonlinear transformation, and it's that nonlinear transformation that increases the linear relationship between two variables. Let me show you what I mean by that. When we perform standard linear regression, the regression equation is equal to the second column here, y equals b0 plus b1 times x. And the predicted value is just b0. The regression equation and the predicted value is one and the same. But if we have to use a nonlinear technique like an exponential model, where the dependent variable is going to be equal to the log of y, or in the quadratic model, we can take the square root of y. And the reciprocal model, we would take the dependent variable, y. And logarithmic model and power model. All of these are valid ways that you can transform the regression equation and allow you to still maintain the relationship between the two variables. Let's look at this in a flowchart form. First, I want to perform regression on the raw data and transforming a data set to enhance its linear. It's a multi-step trial and error process. So I might try the R-squared equation and look at the residual plot. Is it linear? Yes, then I use the raw data unchanged. If it's not, try transforming the variables. So use one of the transformation techniques and perform a residual plot. Is the r-squared values, is r-squared greater than r-squared from the transform data? If the answer is no, then continue to try and transform the variables. If it is, and if it's linear, then you can use that transform data. If it's not, you'll keep going back and trying different techniques. So you'll try different transformation techniques to make this work. Well, let's look at how I might perform this example. I built using the exact same model as we did in the regression class before, but this time, if I show you the manually created data now, I've just got columns x and y, and I've intentionally made this a nonlinear pattern. So when I come out here and I look at the regression results for being able to predict y, I see that my r-squared value is 77, and this is my intercept formula, and everything looks right, except when I look at the scatter plot diagram. For the residuals, you'll see a distinct curve. You see within here how as I move up, it's coming up, and then it's coming down. So there is a curve linear relationship here among the data. And that means the regression formula is one of the reasons the regression formula is not working particularly well at 77%. So what I want to do is alter the value of x. So I'm going to come in here and I'm going to add a math node. And I'll pull this back a little bit. And the output of the math node will feed both of these. This math node, I'm going to say, there it is, the power. I'm going to take the column X and I'm going to raise it to a power of 4. And I'm going to create a new column called new X. And execute that. And let's look at our output data. So now X, you can see the different values it's taking on. 9 to the 4th power, 7 to the 4th power, 5 to the 4th power, and so on. So now, in my linear regression, I don't want to use X, I want to use new X for predicting Y. And now this model, as we'll see, we're going to still be predicting Y, and the residuals is all still the same. So I'm going to go ahead and go to the end of the flow here and execute and open the views. And now my residual pattern, if you look across the 0 axis, is nonlinear, or non-curve linear, excuse me. So the data is now scattered randomly among the positive and negative values. So in other words, by raising it to a power of 4, and I can still look at my formula now and look at the results, and now I've got my multi-R squared up to 0.98. So I've got a different formula and a different slope for the line, but my R squared value is significantly better by doing this transformation of the data. So it's just a little trick at the end of the day that makes our linear regression formulas more accurate. Now, what you can see I've done here is I've recorded my results, the R squared value, through different techniques that I tried. I actually tried using a logarithmic version, I tried using the square root, and with each case I recorded my coefficient of determination. And so my R squared value, I tried log, like I said, exponents, I tried raising it to multiple different powers, and I finally got one that actually produced a linear result with a high R squared value. That's what I mean by trial and error. This process of transformation is one that you're not just going to try one thing it works, you're going to have to try many different things and see which one actually produces the best results for you. That completes this chapter of the class. Feel free to move on to the next chapter.